Thank you. Thank you for the introduction, Farouk, and thank you, Mark. I'm very pleased to consider a great honor to be speaking at the Maud Menten Institute. I'm glad for one reason, is that I didn't know about Maud Menten until I got this invitation, and I don't know why not. Actually, she lived until only 3 years before I got my PhD, and so our lives overlapped tremendously, and I was very impressed how she survived and was wonderfully productive, and in spite of the obstacles that she faced. I thought I had it bad, but wow, you should read what there is to read about Maud Menten. It's really inspiring. I want to make a couple of unpaid announcements. One is that there will be what sounds like an interesting talk by Priscilla this Friday, November 1st. It's coming to us from University of UW at 3:30 in the afternoon. And Priscilla, in case anybody doesn't know, anybody not heard of Priscilla? Well, he's one of the legends already, although he's very much alive in our field of applied math and also in stochastics and statistics, and what Prissy doesn't know about, well, I don't know. So he's talking on the topic, why prove theorems? So I have my speculation what he's going to talk about and what will be the emphasis, but I'm not going to give away my thoughts, and you can have your own private ones about that. The theme, my theme here for this lecture and this visit is going to be that noise is unavoidable. Noise is everywhere in everybody's data, in everybody's field of interest. And so we should really understand how it affects our models. We should look at our models and see what is there that can be considered stochastic and taken into account. And part of my message is that not to do this is risky, but there's more emphasis for me on you're missing a lot of the fun of modeling if you don't take into account the stochastic aspects, which are there actually in your problem. And the general mode of my attack is to say this is going to be stochastic dynamics taken apart and put back together. What I mean is there is the dynamics, and I think a lot of us, not me, but a lot of you, know a great deal about dynamical systems theory, or particularly in the case of examples that you're working on. And then there's stochastics in stochastic dynamics. And these can be thought of as separately. And I want to say that when you have your dynamics, you can add your stochastics by thinking about it and by following some examples that I will, or one particular example that I will present. And And perhaps I will make some progress. We shall see. So the example that I want to focus on is given by this equation, which is for a population dynamic where individuals in a population which has, let's say, a density U, because it's supposed to be differentiable. And there, in the first term, there are two things. There's U squared, which is a birth rate per capita, is one way to interpret it. Or it could be that it is expressing that the individuals do not find each other easily when they are at a very low level. And so, in fact, the rate of production of new ones is less than it would be with just one, with the exponent 1 on that U. Of course, the next factor, 1 minus U over K, is about capacity of a system to absorb individuals U. And then the minus mu times U is a death term. So mu is the rate of demise of this population in the terms of density. And what we do often mathematically is to so-called non-dimensionalize. And for me, this is changing variables in a certain way in order to focus our attention on the parameter that I am going to play around with, the parameter rho. So rho, arguably in a situation, and I decided I should have a situation, and my situation, which I'm not going to really talk about, but my situation is some kind of insects. And I'm going to say that the temperature is random in the environment of these insects. And so the death rate is random along with the temperature in the environment, which is, it's going up and down day to day the way it does around here. Sometimes being uncomfortable for certain insects and comfortable for other insects. But I'm not going to choose an insect. In fact, I'm going to let you choose the model that maybe you are working with, which is something like this, not exactly, but what I like about this model, and a reason for using it, is that it is of order 3 in X. In other words, there's an X cubed there. And that leads to the dynamics being complex enough that we can use it for what I want to do to it with the noise. So I'm giving away all my secrets. One of them is that that third power of X is crucial, actually, to what I'm going to talk about. So there's our equation again, our model. And of course, you all know this, but I'll say it anyway. If for this model, if rho is bigger than a quarter, then there's only one equilibrium at X equals 0. If it's less than a quarter, then there are two additional equilibria at 1 plus minus 1 minus root 4 rho over 2. And so we call rho equal 1/4 the critical parameter for this model. What happens is that the dynamics change rapidly as rho passes from below rho critical and above and to above rho critical. And that's just what we're going to do. We're going to say that rho is moving, not just fixed, but moving in such a way that it will move back and forth across rho critical. And not only is it going to move, but it's going to move according to a stochastic process. So here there is, and we're going to look a lot at this diagram, it turns out, a bifurcation diagram where the bifurcation parameter is rho. And you see there in red the fixed points in terms of x of the model. And in particular, the upper part of that parabola is points where the system is stable. So we have stable equilibria on the upper branch of the parabola, and unstable ones at the lower branch of the parabola. And then again at zero, we have stable equilibrium. Now, there's another line drawn vertically in dashes at 1/4, and that's our critical point. And then there's another, I'm going to call it a yellow line. Some people say it's a brown line anyway. What does it look like on the screen? The brownish yellow. And that is going to be the center of our stochastic process, rho, when it becomes a stochastic process, which is very soon. Now, I think it's cut, on the screen, it's not cut off. Rho as a Ornstein-Uhlenbeck process. So tuck the first part at the back of your mind and think about a stochastic process that's doing the following thing for each increment of time between t and t plus dt. This process is drawn, let's say back, or drawn to what is called by me rho center, which I'm going to choose to be just above that critical point of rho equals, what was it? 1/4. So rho center is going to be very important for the process. At each step, it gets pulled back at rate lambda toward rho center. And the process has just one other aspect, namely, at each delta t, an increment of Brownian motion is added on. And this will be, and I'm going to often refer to what it is when you code it. So we're going to think of coding this and simulating it. And in fact, simulating both the X process and the rho process at the same time. So I will talk in terms of what happens in an increment of time. And if you do coding, then it will be very convenient because you can follow this very well. I'm going to use this process together with the model for X as a pair of processes. Before going on, I want to make everyone more comfortable with the process rho, which is called an Ornstein-Uhlenbeck process, by saying that one can actually solve this stochastic differential equation and get the expression number 4 that you see there. And then you will notice that if t goes to infinity, we have
Sorry, no more audio.
Oh, that's working. Okay, good. Okay, that goes in your pocket.
so here we are with our what I have called Allee Ornstein-Uhlenbeck model. And the model has 2 components, x and rho. And if you go along the top line, you see what was our original deterministic model with 0 coefficient in front of the noise term. And then the rho equation is the bottom line minus lambda rho minus rho center, and then plus the parameter phi times dw. By the way, I didn't notice, I didn't bring to your attention that there are 3 parameters now in our model. The lambda, which is how much the Ornstein-Uhlenbeck is pulling in toward the center, and the phi, which is how big is the noise. Now, in general, the phi is a tool in modeling, in stochastic modeling, which should not be neglected. The phi can depend on the rho, or on, since we have two variables, x and rho, the phi could thinkably depend on the x and the rho in some models. In this case, this is actually an introduction to a certain kind of thinking, and so I'm going to make it as simple as possible and let the phi be constant. And by the way, what is my problem? Nobody asked. What is my problem? I got by with that for several minutes. My problem is going to be, what is the distribution of the extinction time of this model? In other words, how long will it be until X becomes 0? And this is a quantity which is not to obtain for the deterministic model. And the interest here is that going to be very close to the same, or is it going to have at least the same mean, which actually it doesn't, and how will this, what will be the distribution, in fact? They're going for broke here, not just the mean and not just the variance of the random variable extinction time of population, but the whole distribution is what we're going to want. And so with that in mind, I want to introduce 2 additional stochastic processes, which are called G plus and minus, and they are related to rho t by that familiar expression, a half 1 plus minus square root 1 minus 4 rho t. And in fact, we will plot those, and we will see that they are essentially the processes which are the excursions away from the critical point, the excursions. Of course, those processes don't exist on the when rho is here. Those are complex numbers, so we just say they don't exist. But they do exist as real life important processes in our story when the sample path of rho t is below 1/4. But more about that a bit later. Now, as I promised, we're back to looking at our bifurcation diagram. And so I will say again that the paths of rho t are centered at the yellow vertical line, and they are going to move to both sides of the critical point. The processes G and G plus are also going to come into it, but not right away. Now, what is this? This is a sample path. A sample path of our bivariate process rho comma t, which can be plotted and on the same page, you might say, the same plot as the bifurcation diagram. And admittedly, this miracle has been arranged by a certain connivance of forethought, but it's a very nice thing to look at, because not only can we see for each point in the X row plane in which direction the field of the dynamics and the stochastics are pushing the point, but we can see them on the same plot. And this gives a certain insight, which I think is really valuable. So you can travel around the two-dimensional space X row, thinking, this doesn't work, but thinking in one side of your brain about that force field, or that guidance field, which is guiding where the point goes, and also see what has happened in the past, and all at the same time. So in this particular, think of creating this by first taking a sample path of Brownian motion, and then feeding it into the pair X comma rho, and then you watch what the point does, step by step. Now you see we have started the point at row center, and X equals 1/2. And where does it go from there? Well, in this particular sample path, there is a random step to the right, which is quite large. And what does that do? Well, it puts the moving point far into the danger zone for extinction. What happens next is that both the stochastics and the attractive allure of the unstable, not the unstable limit cycle, but the center of the row process pulls it back. But it doesn't go quite over into it does not go quite over into the region of on the inside of the parabola. And then what happens is, at random, the path goes to the right again, and all the time we are in the part of the force field where where we have just, at least most of where we have just the attracted at 0. The plate is pulled down, and we will see that this is not the only thing that happens. Here is another sample path, and we pulled these sample paths more or less in succession. We were in a hurry. We didn't take time to select these sample paths. The next one happened to go to the left, first of all, and then it went into the region where a lot of things are going on. Namely, there is attraction by the stable equilibrium of the X process, and there is at the same time the randomness of the row process. And I didn't mention, but the row process has also an attractive term in the row center. So when think in terms of alternate up-down movement and then right-left. So you have an up-down, which is just the X, and so that's just the dynamics of the X process. And then you have the back and forth row, and there you have two things, both the stochastics is coming in, and also the attractive force towards the row center. So see if you can do that. What's happening in terms of our goal, which is to understand what is the distribution of the extinction time. Well, if the process spends, the more time the process spends sort of messing around doing its dynamics, like this sample path does, the more time is going to be tied up to the extinction time. So it's a delaying tactic on the part of the overall field to have the sample path mess around on the left side of the diagram, and before it goes to the right side, where it just plummets to extinction. So maybe one or two more of these. Here's another sample path. In this one, you see that the noise manages to break the barrier unstable part of the dynamics, and actually goes across the unstable branch of the parabola. And here's another, I think this is the last one where something quite different happens. And it looks like, again, in a different way, something uses up a lot of time before extinction happens. But there's a definite pattern there that you can see, which is the first few steps of the sample path tend to be rather decisive for how the whole thing evolves. And then there's the middle part, and then at the end, it's same old story. Oh, there was one more, but let's not dwell on this one. And now we have plotted with sample paths. Again, we have sample paths, but now we have plotted this and those separately. So the top line is a selected sample path of X row, such that we have a rather long, the sample path of X is in red above, and the sample path of the corresponding row is the second line. And you see, and the black line in the first row, the black curve is a deterministic, the solution of a deterministic equation. So you can compare what the stochastic path is doing with the deterministic one. And in this case, you see the stochastic path has spent a lot of time going around. In this view of it, you can see in the bottom two rows a blow up of the part of the diagram where the red line, which is the path of the X process, you see it's between the two yellow clouds. You see the clouds, it's staying up in the clouds. The clouds are holding it up. So the bottom yellow sample path, which is the G minus process, which is occurring because actually the row is small enough. The G process is kind of repelling the X process, you might say, and that's because it's an unstable equilibrium in fact, but a stochastic unstable equilibrium. And the upper yellow curve, the G plus, is helping it out because that's an attractive stable state. And And so it's keeping our happy red sample path of X void up in the clouds for quite a while. And that's how the extinction gets postponed by the noise. Oh, okay, that's fine. Oh, I see it escaped. Okay. It's- Maybe I'm stochastic myself. Okay. Now, so that previous slide, the sample path was selected by us to show a point. And this one is also selected by us to show a point. Namely, it is quite possible for the time until extinction to be shorter than the deterministic one. And this shows how that can happen. Namely, the yellow clouds, which you see up there in the first row toward the right, the yellow clouds appeared too late. And so our favorite red sample path started out with the row pushing it up at the very beginning, and it had no time to recover. And so our stochastic path of X actually went extinct quite a bit before the deterministic one. So both things can happen. And the question remains, what about the whole distribution of the time until extinction? I promised that there would be results about that. And sure enough, here they are. So what we did, these are histograms from 50,000 simulations of that bivariate process. And what we plotted is histograms of the resulting time until not extinction, but we took as a stand-in for extinction the time until the X path goes below 0.4, because we discovered that, in fact, we save a lot of computing time that way, and it never does recover if it's gone that low. So, and why the two different plots? Well, one is for lambda equals 0.01. And you see that it is an exponential looking curve as a probability distribution. Of course, the histogram is used to approximate the distribution. And there's a problem there of how long do you have to simulate it in order to get a good approximation that the histogram is a good approximation of the distribution. That's a different problem. But it is quite clear that with lambda bigger, the distribution of that time to extinction is pulled closer in around the around its own mean and also around the deterministic one. But when lambda gets smaller, then it spreads out. So just from taking two values of lambda, you can see which way it goes. Now there are questions of the form, what happens in the limit? And I think these questions are not very interesting, but you can prove theorems about what happens in the limit. Okay, but perhaps the practical answers come not from what happens in the limit, but from looking at particular histograms for parameters you're interested in after calibrating this with your particular application. And here are histograms comparing two values of the noise. So the one on the left has the phi, the constant in front of the dW, or the standard deviation of the noise increment is 0.001, and so that would be of the two the smaller noise, and the larger one is phi equals 0.01. So a factor of 10 between them. And we see that with, well, in both cases, we see that, in fact, the mean, which is the red, I'm not sure if it's red or not, but anyway, you can see better than I can, I think. The dashed and dotted vertical lines are the mean and median of the histogram, and the solid line is the deterministic value for comparison. So, the mean of the stochastic model is, in both of these cases, quite a bit less, which seems to go the other way from what we were thinking when we were looking at those sample paths. We were thinking, well, in the sample paths, we're wasting a lot of time fooling around in this bifurcation diagram. And so it must be that more time gets used up. But it turns out, if you look at the histogram, it goes the other way in the cases that we computed. And here, for contrast, is another histogram, and you see that here we chose row center to be below 1/4. So what does that do? Well, what that does is that it again gives us a it again gives us a histogram that looks like it could be an exponential distribution lurking there. And if you think back to the bifurcation diagram, this would put the yellow line on the left side of the critical 1/4. So it means that it's more in the danger zone. But what we found, and we're working on this now, is that in the case where row center is less than 1/4, something even more interesting happens, namely the nucleins of the two processes intersect. And when the nucleins intersect, we have a fixed point of the whole system. And that fixed point of the whole system actually causes a lot more time to be spent in the neighborhood of that fixed point, which is the intersection. So the whole new story about that, which I'm not telling today, because actually I'm almost finished with this talk. The recap is like this. First of all, not only mathematicians have mathematical ideas, also chemists like Menten have mathematical ideas. And we have ideas when we're thinking about real problems, which is another one of my themes, although not the main one today. So point 2, a parameter made into an Ornstein-Uhlenbeck process nicely models environmental noise. Point 3, a bifurcation diagram and sample path plots may be combined in a fusion of stochastics and dynamics, which does not start with taking another PhD in stochastic process theory. It is more accessible than that. It is just thinking what the process with the stochastics and the dynamics both in hand does step by step. That's all one needs to do stochastic dynamics. And finally, distributions of functionals of sample paths, such as first passage times, which I talked about today, for selected parameter values may be estimated by histograms. Now, there's a special point about that. It wouldn't have been possible 5 or 10 years ago to do this computation of histograms. The computers weren't fast enough. So this is an avenue which has recently opened to us population dynamics modelers that we can actually get distributions of functionals of stochastic models with the computer power we now have on our laptops. Thank you very much.
The motivation where we're looking at that bivariate process, I had a good intuition for why the extinction time was longer than that of the deterministic process. But then when you showed us the histograms, the other way.
Yeah.
Can you help me understand? Like that now seems counterintuitive to me a little bit. Like, can you get
Let me repeat. Yeah, let me repeat the question. Exactly. Yeah. So the question is, isn't it counterintuitive that we understood somehow that the more time is going to be used up before extinction with the stochastic model than the deterministic model, but it turned out with the distributions, as I showed you, that it turns out the other way. Yes. Yes, and this is another point in my mind that you can't tell by guessing. You have to actually look at many, many, many sample paths in order to see how the distribution is going to come out in the long run. So yes, thank you for pointing that out. Right on.
Online. And it says, how do you select these parameters such that the distributions can be, the range of the parameters be found analytically? It's already outlined how this is done, as I was a few minutes ago.
Well, I can claim little responsibility for choosing those parameters because my co-author chose them. But he chose two that he thought would show very different results, so an order of magnitude apart. And if one is, but it does show, the ones that we happen to choose, they show a couple of things. They show, first of all, that it's possible to get this information for a large range of parameters. And secondly, the particular, if you, oh, hi, Anatita. Friend of mine, UBC. If you have two different parameters, that tells you the direction. And it's not necessarily that all functionals of sample paths are monotonic. They could be unimodal or bimodal or whatever, but there are some which we can tell pretty well by our intuition, together with a couple of examples, which way it's going with the parameter. So, did I answer the question?
I think there is a follow-up. Would they have any physical meaning or biological?
The answer is yes. And please email me and we can discuss this. Yes, thank you. Sounds like you're getting interested. I like it.
Question for Matt. Adam, walk by hand on the screen here. Cindy, yeah, so.
I know you said that you weren't interested in limits, but as lambda goes to infinity, the system should converge to a univariate Statenovich, SDE, that, oh, it sounds interesting, can be analyzed and for which the effective bifurcation point should depend on the noise intensity. Does this provide any useful insight, or is the limit somehow singular? The answer, Adam, is, and this was a postdoc. Adam was a postdoc with me in the 1990s. So thanks for your question, Adam. Hi. And actually, we can discuss this tomorrow. We have an appointment tomorrow. But just for the audience, what can I say? I think I'd better not try to say too much, but you're right. Sometimes it's really interesting to take a limit, and it could well be that this is one of those times. Thanks.
Okay. So let's say thank you.